Ask any developer who watches their open source dependencies for danger, and most will give the same answer. GitHub does that automatically. Here is the uncomfortable part. In June of 2025, GitHub switched that watcher off by default for new public repositories, and most maintainers never noticed. If you created a repository since then, the protection you think you have may simply be off. That switch sits inside one of 6 free security settings. GitHub itself is asking maintainers to turn on. But here is the version of that list nobody tells you. 5 of those 6 settings are doorbells. They ring. Only one of them is a lock. This video is the machine behind each one. The list comes from GitHub's own security team, 6 settings, all free, and GitHub claims the whole pass takes under half an hour. A security policy file, private vulnerability reporting, secret scanning with push protection, Dependabot with dependency review, code scanning, and branch protection. To GitHub's credit, the same article admits these will not make your project unhackable. They close the easy doors. One caution before we open anything up: free here mostly means free for public repositories. On a private repository on the free plan, you get the dependency tooling and the policy file, and not much else. Now, a checklist is not understanding. The real question is, what actually happens inside GitHub's machinery when you flip each switch? So we will follow the data itself, from a stranger's discovery all the way to a refused push. Start with the strangest fact in the whole system. The first 2 settings never touch your code. They decide where bad news lands. Imagine a security researcher finds a real flaw in your project. If you have given them no channel, their default move is a public issue, often with a working proof of concept attached. That is a 0-day published in your own issue tracker. The security policy file changes nothing about the vulnerability. It is a routing file. It tells researchers where to knock, and GitHub simply surfaces it by file name convention. Private vulnerability reporting then builds the private room. A submitted report becomes a draft advisory that only you and the reporter can see. You can open a temporary private fork to write the fix, because a public fix commit is itself a public hint of the exploit. And when the fix is ready, GitHub can issue the flaw an official CVE identifier, typically reviewing the request within about 72 hours. Here is why that pipeline matters beyond your own project. Publishing that advisory pushes a record into the GitHub advisory database, and that record is not prose. A CVE names a vulnerability in the abstract. The database entry adds what a machine needs, the exact ecosystem, the exact package name, and the exact range of affected versions. Human curators do that translation, and lately, they are drowning. In May of 2026, GitHub's team published more than 1,500 reviewed advisories in a single month, roughly 5 times its typical output of 2 years earlier. Private reports across the platform went from around 550 a week in January to more than 3,000 a week by May. Hold that image, a growing library of machine-readable danger. Because the next setting is nothing more than a lookup against it. Dependabot begins with something called the dependency graph, and the name oversells it. It is a parser. It reads the manifest and lock files where your project declares its packages and extracts names and versions. It does not analyze your code. The alert logic is then almost embarrassingly simple. Your graph says you use this package at this version. An advisory says versions below some number are vulnerable. The 2 ranges intersect, so an alert fires. Notice what that is not. It is not proof you are exploitable. Nothing checks whether your code ever calls the vulnerable function, which is why alert fatigue is real. But notice the quiet superpower too. An alert can fire because a new advisory landed, not because you changed anything. Your untouched frozen repository can wake up vulnerable tomorrow, because what changed was the world's knowledge about it. And this is the setting whose default quietly flipped. Since June of 2025, new public repositories start with the graph off. GitHub's stated reason, of roughly 100 million repositories with it on, only about 6 million had any write activity in 3 years. The watcher was mostly watching graveyards. 2026 added 2 stranger defenses, and most coverage has missed both. The first is a second list, malware alerts. Not, this honest package has a flaw, but this package is the attack, fed by a shared open source feed of known malicious packages. You have to opt in. The second is the best mechanism on this entire list, because it does nothing. Look at how long a poisoned package actually survives. One major attack this spring was caught in under half an hour. Others lasted 2 or 3 hours. So in July of 2026, Dependabot's default became wait 3 days before proposing a routine version upgrade. Security fixes still come through immediately. No detection, no intelligence. It just refuses to be first, and lets the world's scanners burn the attack down before your repository reaches for it. One caveat, and it matters more every month. The cooldown only gates Dependabot's own pull requests. It does not stop you or your coding agent from typing an install command. The next switch watches every push for secrets, keys, tokens, credentials. It guards a line that cannot be uncrossed. The public side of GitHub is watched by automated scrapers, and honeypot experiments repeatedly find that a leaked cloud key is discovered and abused within minutes. So once a key reaches a public repository, deleting the commit is theater. A pushed key is a burned key, and the only real fix is revoking it. This is why the industry did something remarkable. It redesigned credentials to be machine findable. Since 2021, GitHub's own tokens carry a recognizable prefix saying what kind of token they are, plus a built-in checksum, so a scanner can confirm a match without calling anyone. And when scanning finds a partner company's key, GitHub does not revoke it. It sends a signed alert to the issuing provider, whose job is to kill the credential at the source. Detection, though, always arrives after the line is crossed. Push protection is the half that acts before, the server rejects the push itself, and a secret never becomes public. Anyone with write access can bypass it with a stated reason, and the bypass is logged. Real friction, not a wall. And the pressure on this switch is rising. One scanning vendor has found the same signal in 2 separate years with 2 different tools. Repositories using an AI assistant leaked about 40% more secrets than baseline. A year later, commits co-written by a coding agent leaked at roughly double the baseline rate, correlation from a vendor selling detection, but the direction repeated. The 5th switch is the only one that truly reads your code. Code scanning, powered by an engine called CodeQL, starts with a strange move. It does not scan your files, it converts them. Your codebase becomes a queryable database of facts, the syntax tree, the types, and how data flows between them. Hunting a whole class of vulnerability stops being a text search and becomes a database query. The idea that makes it work is taint tracking. Untrusted input is marked tainted, and taint survives transformation. Trim it, combine it, wrap it, the result stays tainted. The engine then hunts for a complete path from a source, where untrusted data enters, to a sink, where it becomes dangerous, a database call, a shell command, a rendered page, with no cleaning step in between. So the alert is not, this line looks suspicious. It is a full route, hop by hop, that a human can actually review. On public repositories, an AI reviewer called Copilot Autofix then reads that route and proposes the patch. Free, no subscription required. The honest limits: it speaks only about 10 language families, and it only finds flaw classes somebody wrote a query for. Novel logic mistakes walk straight past it. Now notice, every setting so far produces, at most, a signal, or a stop you can wave yourself past, and a signal nobody is forced to act on is just a notification. The 6th switch is different in kind. Branch protection is enforced on GitHub servers. When you push, your machine proposes an update, and GitHub either accepts it or refuses. There is no local hook to delete, no way to argue with it. Require a pull request, require reviews, require named checks to pass, and the doorbells change meaning. A failed dependency check stops being a red mark you can merge past and becomes a closed gate. Block force pushes, and history cannot be quietly rewritten. This is the setting that converts 5 signals into 1 refusal, and it ships with a trap. Under the classic rules, administrators are exempt by default. On a solo project, you're the administrator. The lock you just installed does not apply to you until you say so. Time for the honest limit, because the record of real attacks is brutal. The XZUtils backdoor. A patient attacker spent years becoming a trusted maintainer, then hid the payload in plain sight, disguised as binary test data inside the repository itself, while the script that armed it never appeared in the repository at all, only in the release files. The chalk and debug attack. A maintainer typed their password and one-time code into a perfect fake login page, and 16 minutes later, malicious versions of packages with roughly 2 billion weekly downloads were live. The attacker never touched GitHub, and the estimated takings were under $1,000. The Axios attack, the lead maintainer's own computer was compromised directly, and the NX attack did something new. Its malware invoked the AI coding agents already installed on each victim's machine, and had them inventory the sensitive files worth stealing. The first widely documented case of an AI agent drafted as a burglar scout. Here is the pattern. Every one of these attackers arrived holding legitimate credentials, or shipped a package that did not match the public source. All 6 settings assume danger comes from outside the trust boundary. These attacks walked in through the front door. So were the 6 settings pointless? Here is the twist that makes this whole story worth telling. In 2 attacks of this kind, NX and a wave this spring against the TanStack packages, the root cause was a misconfigured automation workflow. And CodeQL has a named, ready-made query for exactly that bug, free on public repositories, available months before either attack. Nothing required anyone to turn it on. That is the real lesson, and it is bigger than GitHub. On one vendor security benchmark, models raced from about half to about 95% at writing code that runs, while staying roughly flat near half at writing code that is safe. Curated tasks, not production code, but the gap is the point. As AI writes more of the world's software, the tools that catch what slips through mostly exist, cost nothing, and ship switched off. 5 doorbells and 1 lock, waiting for someone to bother. Flipping them takes half an hour, says GitHub. Understanding what you flipped, that was this video. The full free course on how AI actually works is linked below, next to the practical season. Subscribe, and the next time a default quietly flips, you will hear about it here.